Hi, this is a lecture on an overview about double integrals. We'd like to launch into the evaluation and applications of double integrals. But as a quick review, I would like to give you this particular lecture. So we'd like to understand the double integral from scratch. So let's begin. Where does one apply a double integral? One of the easiest situations where you can apply the double integral is to find the area of a lamina under a curve. So here you can see we have got a region which is bounded above by a curve and bounded below, let us say, by the x-axis. And this area can be estimated provided you know the equation of the curve. If the equation of the curve is simple, then the evaluation of area becomes extremely easy. On the other hand, if the curve has many features, writing an equation would be very difficult, and even when you write the equation, evaluating the double integral may be very cumbersome or sometimes not possible in a closed form. A second situation where you can apply the double integral is in the determination of volume of a solid under a surface. We can use double integrals to determine the mass of a lamina. In this case, the lamina is on the xy plane. But in order to do that, you will know that you must know the density function of the lamina. Once we determine the mass, center of mass is just one step away, and we can develop the double integral formulas for that. And then one more case where we can apply is to find the moment of inertia of a lamina. So there are plenty of other applications which arise in science and engineering, but this is only to motivate you to tell that double integral is a very, very valuable tool. How does a double integral appear on paper? So you can see on the screen three double integrals with different variables being used. In the first case, f of xy dA, second case f of r theta dA, and third case f of uv dA. Now this dA is called the area element, which arises when we divide the domain R using a grid pattern. The grid pattern will decide which type of integral you will consider. So we'll come to those issues, how to create a grid or a mesh for the region. But let us not get confused anywhere. We must understand every bit of this display. So first we have a double integral operator. We've got a function of two variables. Then there is a dA, which is the area element. So dA is the area element of an element in the grid. Now, how does one interpret the result of a double integral? That is, once you perform a double integration, how do you interpret the result of that? Now, this is not an easy question. If you consider double integral f of xy dA, then the output depends upon what f of xy stands for and what the region R is. The region R provides the limits of integration, but f of xy is that very crucial part of the process which alone will decide what will be the nature of the output. For example, if f of xy represents the density function, then the result of double integration is the mass of the region R. Now this comes from a very simple principle of physics. On the other hand, in a very simplistic case, if you take f of xy is equal to the scalar 1, then the result of double integration is the area of the region R. We'll come to these issues when we get into the details. What are the various forms of a double integral? There are many, but two of them stand out. One is called the Cartesian double integral, when the region R of integration is on the Cartesian plane. Now that is a region R that you can see on the Cartesian plane. Two, there is something called a polar double integral, where the region R is bounded by polar curves. So we must have a very good understanding of what polar curves are. So that you can see is a polar region, and you can compare it with the Cartesian region above that, and you find that the treatment is completely different. And just don't panic. Polar double integrals are generally considered difficult by students, but after you listen to this lecture series, you will have no worries. Now, this is how a Cartesian double integral looks like. Double integral f of x y dA over R. R is called the region of integration, and that dA is either dx dy or dy dx, because in the Cartesian case, the region is divided into a rectangular mesh. A rectangular mesh is obtained by using vertical and horizontal lines. And obviously, if you take a small element of this grid, it's a rectangle. Let us say the width is dx and the height is dy. Then area of a rectangle is length into the width. So it can be dx dy or dy dx. Of course, when you get into the serious business of double integration, you must have the sense of using either dx dy or dy dx. You cannot randomly take any one of them except in one particular case. So how do you evaluate a Cartesian double integral? Now, when the double integral comes with limits, so you can see here that in the first case, the inner integral, that means the integral closer to the function f of xy, has got functions of x as the limits, alpha x and beta x. So these correspond to the limits for y. Therefore, the first integration will be with respect to y. So I have highlighted dy. So whenever you have inner limits as functions of x, the order is dy first and then dx. Conversely, when the inner limits are functions of y, then the order of integration is dx and then dy. So this is a very crucial way of beginning to understand how to evaluate double integrals. What about that case when the outer limits as well as inner limits are both constants? Then you can use any order, dy dx or dx dy. But if one of them is easier, you choose that one. Now, how do you evaluate a Cartesian double integral? When the double integral comes with limits, you know what to do. What happens when the double integral does not come with limits? Then you use this particular principle. That means if you are able to recognize the region as an Rx region, now what that Rx region is unknown to you. I'm going to explain that separately. If your region can be categorized as an Rx region, then the order of integration will be dy dx. That means the y limits will be alpha x to beta x and the x limits will be a to b. On the other hand, if you have classified the region as an Ry region, then your order of integration will be dx dy, which means alpha y and beta y are the limits for the variable x, and a and b are the limits for the variable y. So there is a big question mark here. What is this Rx region? What is an Ry region? How do we understand them? As I told you, I'm taking you on a quick tour of what is going to come in double integrals. Therefore, several questions remain to be answered. So what are Rx regions and Ry regions? Look at this region. This region, let us say, is bounded by two curves, a blue curve below and a red curve above. I know the equations, of course. And you can see that I'm able to see this region completely within vertical parallel lines. So if any region can be expressed like this, we say the region is an Rx region. How to fix the limits, I will explain in my next lecture. Conversely, suppose we have got a region R between two curves, where we now talk about a left curve and a right curve. The left curve is in blue, the right curve is in red. So this region can be framed within horizontal lines, as you can see. So in other words, Rx regions and Ry regions are rotations of each other. So how to fix the limits for an Ry region or an Rx region will be explained very soon. But this is the principle behind Rx region and Ry region. What do you mean by changing order of integration? This is a very exclusive double integration principle. Suppose you look at the first case A, the left hand side integral is the original one. And suppose you are not able to begin the integration or you land into a complicated situation. So the dy dx order may not be suitable for this situation. Then you transform the problem in such a way that the order of integration is not dy dx but dx dy. If you remember the previous slides, the dy dx order comes when you are expressing the region as an Rx region, whereas the dx dy order comes when the region is Ry. In other words, changing order of integration means expressing an Rx region as an Ry region and vice versa. The second part is Ry to Rx. So this is a very, very important principle which many students are scared of. Then comes the polar coordinate system. I had already told you that there are two popular double integration principles. One, Cartesian double integrals, two, polar double integrals. Before we go to polar double integrals, we must know what is the polar coordinate system. Now, students who have studied coordinate systems in the lower classes will know that creating a polar coordinate system from a Cartesian coordinate system is pretty straightforward. Suppose you take a point P, which you can see as a black dot. Suppose the coordinates of that are x, y in the Cartesian system. Now, join O, the origin, to that point and call that length as R. In other words, this R is a right angle triangle, the hypotenuse of a right angle triangle. Then simple trigonometry. Suppose theta is the angle between the radius vector and the x-axis. Then cos theta gives us x by r, sin theta gives us y by r. Therefore, x will be r cos theta and y will be equal to r sin theta. I think anybody who knows basic Cartesian geometry and trigonometry can understand this. Now just see what happens now. You can see on the right hand side, x is equal to r cos theta, y is equal to r sin theta, which has been explained from the diagram. Now you find the Jacobian of this transformation, dou xy by dou r theta, and these are partial derivatives. The first row is dou x by dou r, second row is dou x by dou theta, second row is dou y by dou r, and the next one is dou y by dou theta. So when you expand this determinant, you get r cos square theta plus r sin square theta. Therefore, the Jacobian is r. So please just keep this principle in mind. Every time you change a coordinate system, it need not be Cartesian to polar, it can be Cartesian to anything, or one coordinate system to another coordinate system. You must always keep your Jacobian in hand, because we are going to use that in the conversion process. Now I told you in the Cartesian case, the grid design is consisting of rectangular blocks. Whereas when you go to the polar coordinate system, the grid pattern is different. You can see that there are no more rectangles, but this particular grid consists of radial lines that you can see in red starting from the origin, and then concentric circles which are shown in blue. So between the radial lines and the concentric circles, you get not exactly rectangular, but rectangle-like elements. It's not a perfect rectangle, but in a microscopic scale, they appear to be rectangles. So you should understand what is the Cartesian grid and the polar grid. Cartesian grids, once again, I want to tell you, consists of horizontal and vertical lines, and the area elements are perfect rectangles. Whereas in the polar grid, the area elements are not perfect rectangles, but that is what we are going to use. How do we transform from Cartesian to polar integration? First of all, when do we convert? That's the question. Of course, there's another big question, why should we convert? So I'll come to the question of why we should convert when I take up the polar coordinates system for double integration. But let me tell you the context when it is done. When the region of integration is bounded by polar curves. Polar curves, not many of you study in detail, but circle is one of the simplest of the polar curves. Then you can have lemniscates, you can have cardioids and other polar curves too. But it's very easy to explain polar curves through circles. And how do you do it? Suppose you are given a Cartesian double integral f of x y dA, and you find that this integration is difficult. Maybe because the region is not so convenient, or the function f of x y is also not that very favorable to integrate. So under certain conditions, you convert the Cartesian double integral into a polar double integral. So f of xy will change to g of r theta because r and theta are the polar variables. And you know that dA has gone, and in its place r dr d theta has come. This r, if you remember from the previous slides, is the Jacobian of the transformation when you move from Cartesian to polar. So please remember, this is a very, very useful result. What else is going to happen now? Is there something else beyond polar coordinate system? Yes. Not all double integrals can be evaluated in the Cartesian or polar. Sometimes you may have to double integrate over a totally new domain. All that we need is a transformation, and when the transformation is available, we can evaluate certain types of double integrals. I'm going to give you a quick survey of how to draw curves, because without drawing the region, you cannot analyze and then fix the limits. So we need a special session on drawing curves. You must know the art and science behind fixing limits of integration and by analyzing the region of integration. So after the region has been identified, you have to see whether it can be done in Cartesian or in polar or in some other coordinate system. So if it is Cartesian, you must know whether it is an Rx region or an Ry region. If you are going to evaluate in polar, how do you fix your R limits and theta limits? If you are moving to some other coordinate system, then how do you understand the geometry of that? When should one think of changing the order of integration? This question was partially answered by me. Whenever the original integral does not permit, in fact, to evaluate, then by changing the order of integration, sometimes you may be lucky enough to evaluate it. When should one think of transforming to polar? This was also answered partially, when the region boundary consists of polar curves. But we need a lot of visualization through examples. And I'm going to give you detailed illustration of each concept through examples. And there'll be a special presentation on the application of double integration, because once we evaluate a double integral, if you do not know that it is being applied, such an effort will be of no use. So dear friends, this is what double integration in a bird's eye view is going to look like. It's going to be interesting, provided each of these questions that I have displayed are answered systematically and in detail. Thank you.